In software engineering, we are talking about software reliability. For any product, it can be a hardware, it can be a software. The reliability of a software product, that means reliance, that is the trustworthiness, that is the availability, possibility of availability. So mostly the users, they want, normally in the industry, but even if you are a single person, everyone wants quality, and reliability is one of the key of any product quality. Whether you take the Forbes, whether you take ISO 9126 or any other quality parameter, you will see that all these frameworks of quality will involve reliability as the key. So the user, they don't only are satisfied by, okay, reliability is there. They want numbers. Before buying, they want certain quantitative estimation. They want mean time to failure. They want mean time to repair. They want mean time between failure. They want availability, numbers. So the major problems in reliability measurements, the first thing is that in the software, mainly, the errors, they are not occurring, or they do not cause failure at the same frequency or severity. That is, if you are a cricketer and you are playing, maybe in one match you can hit 6 sixes in an over, but sometimes you may get bowled in the first over. This is the scenario of software. So measuring the latent or the hidden errors alone will not be enough in case of software, because the failure rate is generally observer dependent. You are observing different errors, I am observing different errors. What are the definitions of software reliability? The software reliability definition as per IEEE standard is software reliability is the ability of any system, component, software, product, anything. So software reliability, wherever the software is involved, so the ability of these whole to perform its required functions, that is the functions are expected from this particular product. So the ability of these system to perform its required function under stated condition for a specified period of time. That is, if I say this software should work for 1 year, software reliability is that it will work for 1 year in certain stated condition. That is, it will provide all the functionality for that stipulated time which we have decided, which we have defined under stated condition. There can be multiple conditions. Okay, so this is also the probability. I'll just come to that. But informally, the software reliability is all about product worthiness, trustworthiness, and dependability. How much you can trust, how much you can depend on that particular product for a specified time under stated condition. So again, the definition of software reliability is the probability of the software product working correctly over a given period of time. So time has to be there, correctly has to be there, and probability has to be there. So the definition should consider the probability, first thing, of the product working correctly, the second thing, over a given period of time. So these three things are key. Intuitively, a software product which is having a large number of defects is unreliable. Software product with less number of defects is reliable. So what it says is that the reliability of the system or the software product will improve if the number of defects is reduced. Difficulty in software reliability measurement, because there is no simple one-to-one or mathematical estimated or probabilistic, any kind of relationship between the observed system reliability, which is also called as the operational reliability. Because in the software, there are number of latent software defects that may be present. Some of the defects may be perceived, some may not be. That is, if you are removing certain part of some errors from a part of a software, which is rarely used, it is not even being used, it will make no difference in the perceived reliability, because this is operational reliability and user observant reliability. The 90-10 rule. So what is this 90-10 rule in the software reliability? See, you have a whole software product. Okay, let us consider that it is 100%. And all these discussion is coming from experimental analysis of large number of programs done in earlier times till now. So this is your software. Only 10% of the part, 10% of the instruction, 10% of the functionality is used 90% of the time. That is, only these functionality is used, is employed, is executed 90% of the time. For 10 hours, 9 hours you will be using this. But the 90% which is remaining functionality will only be employed, will only be used only 10% of time. So this part, which is the 10% part, which is extensively used, is called the core of the program. The unused or seldom used part of the program is a non-core part of that program. That is, we are executing it only 10% of the time. This is non-core. Now it is very surprising. I'll tell you a result. Now this is the part, 90% part, which we seldom use, or only 10% time we use, or 90% functionality. So even if we remove 60% of defect from this 90% part of the non-core, reliability will be only improved 3%. There will be only 3% improvement in the software product reliability. Okay, this is 90-10 rule. So as I said, there is a non-core part, a core part. If you remove error from the non-core part, it is hardly improving the software product reliability. That is 10% you are using always, that is 90% of the time, and 90% of the functionality of instruction you are just using 10% of the time. Now if you remove any error from the non-core part, that non-core part will have hardly any effect or in improving the reliability. So the perceived reliability, it depends totally upon the operational profile, how the product is being used. That is, I may be using a core part, you may be using a non-core part. For you and me, the observed and the perceived reliability totally depends on the operational profile. Where are we working? What functionality are we using in our daily basis? Okay. Effect of operational profile on software reliability measurement. Now, if we select input data, that goes into only correct functions. That is, you are doing something, I am doing something. That is, a software, as I said, only 10% of the part is used 90% of the time. And the 90% of the part is only used 10% of the time. So if you select the data, give the input only in the correctly operated implemented function, no errors will be there. So you can, as a user, you will perceive that the reliability of the software is very good. But if we select the input, if we do the functionality, if we execute the software, where that is the part which is not generally used, and then the errors are evoked. Okay, or you can say those which are not properly used. Okay, we input the data such that function only containing errors are invoked. Then the software reliability is quite high. So software reliability, different users have different way of using the software product. For example, you can be a new user, you can be a maintenance user, you can be an admin user, you can be a privileged user. There are so many, league and categories of usage. So different users use in different way. The defect which show for a maintenance user will not be there for a, say, admin user or say a new user. So as I am saying again, reliability of the software product totally depends on who is using, observer dependent, and you cannot determine it absolutely. Software reliability keeps changing throughout the life of product. How does it change? Because as the software is used, it is maintained, the error is detected, the error is corrected, debugging is done, and then correction is done. Okay, so the error will reduce. But some error may be latent, say they may come some other time. But in general, the software reliability will improve as the errors are being removed. Hardware and software reliability. Now hardware, you can feel it, touch it. Software you cannot touch it. So hardware failures, they are altogether different from the software failures. Okay, inherently. What inherently we mean? Because a hardware is dependent on the environmental conditions. Most of the hardware failures are due to the component wear and tear. That is, the environmental condition, the usage, the extra usage will cause wear and tear. If you see here, some components may not give proper functions. For example, using a car. Now, if you use a car for kilometers, the tire will need replacement, or it will not work, or it will get punctured. So this is the hardware problems. For example, in electronics, a logic gate, it may get stuck on 1 or 0, or the resistor might get short circuited. So these are the general things which we see in hardware. To fix, how to mitigate with the hardware faults, just repair or replace. If you have a spare part, replace it. If you are not having a spare part, you can just repair it, the failed part, and you can use it again. So software faults, they are not like hardware faults. They are latent. They are somewhere hidden, or they will only be exposed when some functionality has been executed. The system will continue to fail unless the code and the design level changes are being done. They are being implemented. Okay, so design code changes are needed to actually get over these software faults if we really require good reliability, software reliability. So as we saw, there are different kind of errors or different categories of errors which are in those hardware and software. So many metrics are there for hardware reliability measurements. These are the maintenance metrics. They may not work good with the reliability metrics as far as software is concerned. When a hardware is repaired, what happens? Its reliability is maintained. That is, that part is not working, you just replace it. Reliability will be maintained. But when the software is repaired, bug fixing or some design changes, code changes, the reliability may increase or it may decrease. Increase because the error is being removed. But we do regression testing. Why? Because one fixing of the problem should not generate or should not propagate various other problems. So one bug can create 3 bugs. One bug fixing can create 3 bugs. So this can increase, decrease. So the goal of hardware reliability is all about stability of that hardware. That is, we want that the inter-failure times, the time between 2 failures, should remain constant. If 10 years is the time, the next time of failure should be 10 years. But the goal of software reliability is reliability growth. We want to increase the inter-failure times. For example, 1 year the problem was there. Next time it should come in 6 months. Next time it should come in 3 months. In software reliability and hardware reliability, the difference, let us see first. This is a bathtub curve. Now, on the x-axis we have time, on y-axis we have failure rate. How many failures will happen depending upon the time. Now you see this blue line. This is like a bathtub you use in your toilets and bathrooms to take a wash. Now this is when it starts hardware, there will be errors, great errors, but slowly these errors will be less. And finally, there will be a straight line where there will be no problems. This is a useful life for that hardware. But once it has lived its life, the wear and tear of that hardware will take place. So now the failure rate will increase. So failure rate first, it will increase, then it will be constant, and then it will again increase. In software, same thing. The errors are too much. We use the software testing and the debugging, and now we deploy or we give the software to the user. Now there will be maintenance activity. Now we will give increment, or we will give some new version or upgradation. Now there will be some errors in the upgrade which has been removed. Now next upgrade, some more bug fixing, some more functionality changes, some more things being done. Next upgrade, same thing is being done. So after multiple upgrades, now the life of software becomes stable, or the reliability is we can maintain. And this goes on and on. There is no wear and tear in the software until there is another software which replaces this software. So this is the time when obsolescence period of software takes place. So software reliability, in this external conditions, environmental conditions are not affecting. Only the internal condition, what are the bugs, defects, even the insufficient memory, even the inappropriate clock speeds, they affect the software reliability. Main thing is how much testing you have done, how much bugs you have removed, and how stable your system is. The hardware reliability is totally dependent on the environmental condition, because wear and tear does happen. In a car, if you're using a car for a long time, the tire needs to be replaced. Now software reliability, you cannot predict it. Okay, if you know the design, usage or stress factor, any kind of factor, reliability cannot be easily numbered. Quantitative analysis is not that easy. But reliability, because we have so many models in the hardware, we can easily predict reliability from the design factors and the physical attributes. Software reliability, you cannot improve it using the redundancy. Okay, because if you have two software, you say, oh, one software is failing, let us use the another software. That is, you have redundancy of the software. But what error will come in first software will definitely come in the second software. But in hardware, if one part is failing, if you have redundancy, you can just replace, because you have an extra hardware. So you can just replace it. Okay. You can have a tire. If some tire get blast or anything, you have a stepney. Software reliability, the failure rates of software components, they are not predictable, as I just say. So, because 10% of the functionality are used 90% of the time. In failure rates, the hardware components, these are predictable. Software reliability, the main cause of failures is design faults. Repairs can only be done when you go to the code and go to the design and then do it. Testing, debugging of design, and also the main code software. Hardware reliability, they can be caused by any kind of deficiency in the design, in the production, and the maintenance. Software reliability, there is no wear out phenomenon. There is no wear and tear. Errors can come any time without any warning by using any kind of function which is never being used. Hardware reliability, they will cause wear and tear. Because a person, if he takes birth, he has to die. So we are hardware, we are machines. Okay, if you understand us as a machine. Now software reliability, there is no equivalent preventive maintenance for software. In book you will learn there are only three types of maintenance. Perfective, adaptive, and only the corrective. There is no preventive. Why? Because when you are making a good design, you are making good code, testing it properly. This is the preventive maintenance only. But hardware reliability, repairs can be made that makes hardware more reliable through maintenance. So there is preventive maintenance in hardware reliability. You can put grease, you can put oil in your car so that it works fine. In software reliability, reliability is not time dependent. Failure can occur anytime, anywhere. Logical path error, some conditional error, or some input, some sensitivity, some sanity error. It can happen. But reliability is time related in terms of, in the case of hardware. Failure rates can be decreasing constant and then increasing with respect to the operating time, as you see here in the graph also. Software reliability, this is the probability of this software for providing you all the function or working in a stipulated period of time under certain conditions. Now, in order to compute it, determine it, estimate it, we need metrics. So we have certain metrics. So software can work properly, it can fail, then it can be repaired. So different categories of software products, they have different reliability requirements. For example, if you see the SRS of a different small, complex, different kind of project, this NFR or non-functional requirement will contain the reliability, and that will be in your SRS, software requirement specification. That is how much reliability is wanted, is required. So a good reliability measure should be observer independent. It shouldn't be observer dependent. So the different people can agree on what kind of reliability is there. We know that the 10% of the functionality or the instruction are executed 90% of the time of usage, and 10% you use only 90% of the code. The first matrix is rate of occurrence of failure in software reliability. So first of all, it is rate. Rate means that is per unit time. First thing is clear. Or per unit something. Occurrence of failure. That is, the failure is occurring. What is the rate of these failure occurring? So it is the number of failures appearing, happening, occurring in a unit time interval. Okay. So we try to find out here that what is the, for example, distance upon the time is speed. So this is the rate of changing of distance. So rate of changing of the occurrence of failure. The number of failures divided by the unit time interval. So the number of unexpected events or the events which are not favorable to the user over a specific period of time of operation is ROC-off. So you can call it, because the number means frequency. So ROC-off is the frequency of occurrence with which unexpected events or role is likely to appear in the software usage while you are actually executing the software or using it. So when we come to the quantitative analysis, the ROC-off of 0.02, what does it mean? It means that two failure are likely to occur. Please understand, it is likely to occur in each 100 operational time units steps. The time you can define, it can be any time, but whatever time you have taken it, the two failures per 100 operational time unit step. This is the ROC-off. So all idea is to just finding out the rate of how much failure occurs. It is also called as the failure intensity metric. Failure intensity metric. POFOD, probability of failure on demand. Probability, that means the value will be 0 and between 0 and 1. Okay. So probability that whenever we are demanding certain service, whenever we are demanding, requiring, expecting certain function from the software is failing to provide it. So the probability of failure when we are demanding, it is POFOD. So this is the probability. POFOD is the probability that the system or the software product will fail when we request a service, when a service or certain function or even its exact appearance is requested. For example, a website is there. When you want to access it, it is not available. Okay, the software product or the website is failing to give its service. So this is the probability that the system or the software product is going to fail whenever we are asking for it. So it is the number of system deficiencies, system problems, system defects given several systems input. That is, when you give certain kinds of inputs, the system failed to fulfill our request for a demand, for our request to get word. So POFOD is the probability that the system will fail when a service request is made. For example, 4 times we asked, only 1 time it provided the service. 1 by 4 is the probability, 0.25 is the probability. Okay, I'll give you one more example. If POFOD is 0.1, what does it mean? That 1 out of 10 service requests may fail, likely to fail. So 0.1, because it is the probability. So it is 1 by 10, that is for 10 events, one will be failing. So this is very important for those systems where the life is at stake. For the safety critical system, POFOD is essential. That is why we are talking about it. Mean time to failure, MTTF. First thing is, it is a mean, it is an average. So we are not talking about one time, we are talking about different time, we are adding them divided by the number of count. So this is the average or mean. Now coming to time to failure. How much time does it take for a system or a software product to fail? That is, car is going fine. How much time it will take that the tire gets punctured or your engine stops working? So this is the time for a particular product fail. So we will not do it for once. We'll try to find out these times, number of times, then we'll take an average, and that is the MTTF. So average time between 2 successive failures, and this is observed over a large number of failures, not one. So the system is working fine, it fails. Now when it fails again, first failure, second failure. Now when we see that the system is working fine, so the time system is working fine till the next time the system is working fine. Okay, so when it is working fine, it's okay, but the time from where it started working fine and time second time where it is working fine is the actual time we're talking about. Okay, so MTTF is not very much appropriate for the softwares, as it is mainly these metrics are mainly made for hardware. So you can just call it as total number of hours of operation divided by the total number of units. So hardware fails due to certain reason, due to environmental condition, due to wear and tear. There are many more inputs to its failure. Every hardware has to fail sometime. There is no, immortality. So this indicates how frequently the component fails. Some component fail, your system will fail. But when the software error is detected and it is repaired, it is not always possible to see that error again. It may never reappear. Mean time to failure. Let us take an example to understand this. Total lifespan of our devices. How many devices? We have to divide that. So let us take an example. Imagine that a production line has a total of 3 devices. So the number of devices or assets are given as 3 devices, and they are of same kind. So these 3 devices, one completely failed at 5200 hours, the device number 2 at 4200 hours, and the third at 5600 hours. Okay, let us try to find out the MTTF, mean time to failure. So what is the total lifespan of the devices? Just add all these, 5200, 4200, 5600. You'll get 15,000. How many number of devices? 3. So just divide this 15,000 divided by 3. So you are going to get 500. And this 500. Please remember, we are trying to find out the mean. So add them, divide by 3. This is the MTTF, 500 hours. Mean time to repair, MTTR. Mean is average. So whatever value will come, we have to take the average. We'll add them, divide by the number of counts. So time to repair. That is, if something gets into failure, how much time it will take to repair it. Okay, this is time to repair. So failure has happened. We are talking about the time to get it repaired. So here the failure has happened. So there is a repair time, and that repair time, when it start behaving correctly now, is the mean time to repair. So this mean means we are going to take the average of various values, not one value but different values, and add, and then we'll find out the MTTR. So MTTR is average time it takes to detect the issue. Mean time to repair is an average time. First we have to detect the issue, then we need to diagnose the problem, and then we have to repair the fault or the error or the bug, and then the system return to its functionality. So this MTTR, mean time to repair, is a maintenance matrix. Please remember, it is a maintenance metric that measures the average time, as I am saying, not one time, but we have to try to find out various time and take the average, required to troubleshoot and repair failed equipment. So this is all about the time it needs for repairing. You can just understand like this. So MTTR is the total maintenance time divided by the total number of repairs. So this is an indication, MTTR, for any kind of organization, that how it respond to any kind of unplanned breakdown and repair them. For example, if there is an electricity problem in your house, it can be from your pole, it can be from your transformer, or it can be from, say, the hydroelectric from where it is coming. So the time to repair will be different in terms of different kind of problem, and to repair it will take different time. So as I said, once a failure occurs, what are you going to do? There will be additional time to fix the fault. So this MTTR is finally the measure, it finds out the average time it takes to fix the faults. Let us take an example to understand the MTTR. This is equal to total time spent repairing divided by the number of repairs. So just imagine that a production line has 3 devices that went down. The first one was down for 4 hours. The second was down for 2 hours. And the third for 3 hours. How to find out the MTTR? So what is the total time spent in repairing? 4 hours, 2 hours, 3 hours, add them. 9. What are the number of devices? 3. Divide 9 by 3, you are going to get the MTTR, which is 3 hours. Mean time between failure. So mean time between failure is, see, first of all, it is a mean. So you need to take the average. So once failure happened, you need to repair it. And then there will be correct behavior. And in between that, there will be some time. So one failure, and whatever time it takes to repair and correct behavior, there will be another failure. So the time between two failure is mean time between failure. I hope you got the idea. One failure, second failure. The time elapsed between these two failures is the time between failure. When we take a lot of these numbers, that is whenever it happens, we combine them, take the addition divided by the number of the, say, values we have taken, count we have taken, that will be mean time between failure. So MTBF, mean time between failure, is the predicted elapsed time between inherent failures of a mechanical or an electronic system or a computer system or a software product during normal system operation. So how can you calculate it? It can be calculated as arithmetic mean, that is the average, that is why it is called mean, time between failures of a system. So 2 failures, the time between it is MTBF. This term is used for repairable systems, while mean time to failure MTTF denotes the expected time to failure for a non-repairable system. MTBF simply total working time minus the total breakdown time and divided by the number of breakdowns in this stipulated time. So just subtract this breakdown time from the total working time divided by the number of breakdowns. So this is going to be MTBF. We can combine this MTTR and MTTF, that is the mean time to repair and mean time to failure, and then you add them, that is the time of MTBF. That is mean time between failure, because something happens, some failure happens, there will be time to get it repaired, and after that the system will work fine until it reaches the second failure point. So if you say MTBF of 100 hours, what does it mean? It means once failure has occurred, the next failure will be expected only after 100 hours of clock time. Please remember, this is not the running time. Just see your clock, that will be 100 hours. Not your system is working when. Okay, the time measurements are real time and not the execution time of the software product or the electronic device, as it was done in MTTF or mean time to failure. So this is the clock time. Just add MTTF and MTTR, you will get MTBF. Now let us take an example to understand MTBF. This is the total uptime divided by the number of failures. And this MTBF, let us take an example. Imagine that a production line runs 130 hours in a week with 4 outages. Means in whole 130 hours, there is 4 times it failed. The first one lasted for 2 hours each. That is the first two, that is 2 hours and 2 hours. First one, second one, 2 hours, 2 hours. Okay. So the first two, they were out for 2 hours or down for 2 hours. And the last two, that is the third and fourth one, they took 3 hours each. So now let us find out the MTBF. So 130 hours is the total working time from the start to end. 130 hours, it is being said that all 4 outages are there. 2 for 2 hours, 2 for 3 hours. The total number of outages time is 2 into 2. First was 4 hours. And the second is 2 into 3, that is the 6 hours. Add them, you get the 10 hours. So this is the time where the system didn't perform. It was not well. Okay. So this 10 has to be subtracted from 130, as I showed you the actual formula. So 130, you have to separate out this 10 hours. So that will be the time 120, and that this is the total uptime. And how many number of failures are there? Okay, you have to divide it by 4. So that the MTBF is 30. So this means that when the operation is live, the average time between the failures is 30 hours. Now let me go a step further. Let us try to find out the failure rate. What will be the failure rate? So as I suggested, 30 hours between 2 failures, 30 hours between 2 failures, like this. Average we have taken. Okay. We will try to find out the failure rate. You just have to take the reciprocal of MTBF or mean time between failure. Failure rate is 1 by MTBF. 1 by 30 is 0.033. Availability. Availability is that if I'm asking for something and I'm not getting it, it is not there. Say if I go to a shop and they provide me momos and soup, and when I asked him, give me chicken momo, he says, I don't have chicken momo. So he has written that he is having chicken momo, that availability is not there. So this availability is very much related with the reliability. So system availability, software availability It also is known as equipment availability, asset availability. This is a maintenance metric that measures the probability. So probability means 0 to 1 will be the value that a system is not failed or undergoing a repair action when it needs to be used. When the system is under failed state or repaired state, it is not available. So we are just saying what is the probability that is not under failed or repaired state. So availability is the probability that the system is applicable for use, is available for use at a given time. So this takes, as I said, it takes into account the repair time and the restart time. This also counts for that. And availability of 0.995. Normally the value of availability will be 0.99, 0.999, 0.9, like this. The availability will be like this. Most of the system which have to be up every time, the availability is quite high. They want really high. So 0.995 means in every 1000, we can write it like this, 995 by 1000. So in every 1000 time units, the system is feasible to be available, or simply system is available 995 times. So the percentage of time that the system is available and applicable for use, we are taking in account both of the planned and unplanned downtime, because sometimes the system goes to maintenance, so it is planned time. Sometimes it just goes down, it is unplanned. So if a system is down, say an average of 4 hours in 100 hours, in total 100 hours, 4 hours it is not working. What does it mean? What is the availability? This is the probability of it is available. Availability is 96%. How do we get this 96%? 96% is, you have to subtract it from 1. As you know, in probability, what do? Happening and not happening, we just subtract with 1. So 1 minus 4 by 100, and that is going to give you 96 by 100, and that is going to be 0.96, or you can simply say 96%. This is how we compute the availability. Availability in different terms, you can also talk that it is MTBF by MTBF plus MTTR. So mean time between failure divided by mean time between failure plus MTTR. So this is also a way you can compute it. So it can also be assumed that availability is the total uptime divided by the total uptime plus the downtime. So availability measures how likely the system shall be available for use over a period of time. So as I said, it considers the number of failure, also the repair time, and this metric is very important when it comes to the system which needs to be available all the time, like the telecommunication system. Let us take a computer example, operating system. If your operating system is not working, then how are you going to play games, Microsoft Word, watch YouTube? How? Your operating system is not working. So it is not available. The system is not available when you are asking for it. This kind of screen of death may come. So when repair and restart time are significant and the loss of service during that time is important, this metric needs to be known up front. Okay, this is all about this discussion. Thank you so much. Take care of yourself.